Okay, today we're going to talk about the phase splitters. And here I'm going to reference a video I made about push-pull amplifiers. So I'm going to put the link probably upper right now. Okay, so as you know, when you have a push-pull amplifier, you need as input to the push-pull amplifier two signals of equal amplitude. That you want to amplify it, but those two signals have to be of the same amplitude and out of phase. So there should be a 180 phase difference between the two signals. So how do you get those? So that's the role of the phase splitter. And there are different types of phase splitters, and the simplest one is the so-called transformer type phase splitter. So that's the one I'm going to start with. So if you look at this picture upper left, you have your input signal. So that's maybe your guitar signal input. Okay, so it's a nice sine wave, and this is your transformer. And the transformer, for the whole thing to work, you need a center tap, and that's the whole key. It's the key to the whole thing, and it's something that you see all the time. There's a center tap to get two signals of usually at the middle. The tap is at the middle, and you get two signals which are out of phase. So if you look at the output between point A and point B, you get an amplified signal, assuming that the turns ratio is so that you get amplification. But you get an amplified signal, and the level of amplification depends on your turns ratio. So here, in this case, the signal is inverted, but it really depends on the innards. I could have equally drawn the signal as being non-inverted. It really doesn't matter. What's important is if you look at the signal between A and ground, you're going to get this signal. So this is between A and ground. And if you take the signal the output signal between B and ground, you're gonna get something like this. And the important thing, assuming that the tap is at the middle, is that those two signals have the same amplitude, but they are out of phase by 180 degrees. That's what's important. Same amplitude and 180 degrees out of phase. So if you look at them, you can also say that this signal is an inversion of that signal. That's another way of looking at it. This is how it looks like in real life, if you will. So this is again your input. This is the output, and here is the phase splitter part. This is the phase splitter, and I'll get back to it. And this is the push-pull amp. And again, I refer you to the video I made about the push-pull amp, and so that I won't go back into the details of how the primary voltages add up in the primary of this output transformer. And watch that video about push-pull amplification. That will explain that process here. And this is the output, so typically that goes into your speaker. And this is the push-pull amp setup. So you have your two tubes in opposition or mirrored. So this is the plate, this is the grid, this is the cathode. So cathode, grid, plate. On the cathode side, you have your cathode resistor for the bias. This is the bypass capacitor, this is ground. So that's your typical setup. But let's focus on the phase splitter, because that's what we're talking about today. So again, we have the transformer, but this time instead of having a center tap transformer, you have a regular transformer, but the center tap, if you will, is done by using a balanced resistor tapped at the center, or two resistors of the same value. So this is the center tap on that resistor. Goes to ground, and basically what happens is that the signal induced, this is like a load for that signal, and the same here. So that induced signal generates a voltage across that load, which is here. So we have this voltage, which looks like this, and you have that voltage, which looks like that, which is a one. So those two signals are 180 degrees out of phase. So this setup with that balanced resistor that's tapped in the middle to ground is exactly the same as having a transformer that is center tapped. Okay, so it's exactly the same. This is probably more practical, I guess. So we just talked about the transformer phase splitter. The problem with the transformer is that it's expensive. So just like everything else, it's not used much because it's too expensive. So we need to have a phase splitter that uses a tube, so it's more active. So it's the single stage balanced phase splitter. So this is the circuit here. So we have our input, which is our AC signal. So here, the input, I have those two, the positive and the reference, the ground. Here is my C1R1, so that's my capacitive coupling. Capacitive coupling goes to the grid of the tube. So the tube has the plate and the cathode. The plate, so it's P, connects to the B plus through a resistor R2, and the cathode. So that's the cathode resistor named R3, goes to ground, and this is, so the output is at the plate and at the cathode. At the cathode, this is in phase, and at the plate it's out of phase. So those are your two signals. One is amplified through this tube, and because of amplification you have the inversion. So this one is inverted and this one is as is. And the amplitude depends on the amplification of the tube, but basically it's an amplifier for this one. Why is this one in phase and that one is out of phase? Well, it's very simple. So we have the plate current, and the plate current is equal to the cathode current. It's the current that goes through like this, that goes through the tube. So VC here, the cathode, is equal to R3 times I. I think we all agree on that. I is the plate current. So VC is equal to R3 times I. And here I probably should have used a small, because this is the whole voltage and this is the whole current, so it includes the DC. So this is the whole thing. So just to go deep into it, so this voltage and I are in phase, so it means that VC is in phase with the input. So this one is in phase with this one, the input. So that's clear. So the other phase, why? Because VP is equal to B plus here, minus the voltage drop. So minus R2 times I, the same I, the plate current. And again, this is the AC plus the DC, because here you have, here I'm showing the AC part, but there is a DC level, both of them. So why is it out of phase? That's very easy. It's because of the minus. So remember, I is in phase with the input, but because of the minus, it becomes inverted. So it becomes out of phase. So this is the 180 shift. And if you only look at the AC component, basically, if you only look at the AC, the VC AC is equal to R3 times I, and the VP is equal to minus VP AC is equal to minus R2 times I. For VC and VP to be equal, the AC part, R3 should be equal to R2. So again, R3 is the cathode resistor and R2 is the plate resistor. So for the two AC signals at the output to be equal in magnitude, you need to have R3 is equal to R2. So this is the full circuit. So this is the phase splitter. It's exactly the same as the previous slide. Phase splitter, input here. Okay, so this is the one that's in phase coming out of the cathode. And the one coming out of the plate is the one that is 180 out of phase. And that goes into your push-pull. That's your push-pull amplifier. And here is the capacitive coupling for one signal, and this is the capacitive coupling for the other signal. It goes to the grid. This is the cathode bias resistor here. Nothing fancy, and again it's the same output transformer setup, just like in the video about the push-pull amplifier. So I'm not gonna go into the detail of that. Okay, so that was the single stage balanced phase splitter. Okay, so now it's time to go into the two-stage phase splitter with two tubes. Yeah, the problem with the one stage that there's not much amplification, if at all. So we turn into the two-tube setup, and thus the two stages. So this is the circuit. It's a little bit crowded, so I'll try to explain as best as I can. Input, it's basically one amplifier here and a second amplifier there, and that second amplifier is gonna have as its input a piece of the output from the first amplifier. That's the idea. So this is V1 valve or tube 1, V2 tube 2. So this is your input. So that's your guitar signal. Goes through the coupling capacitor C1 with a resistor R1, goes to the grid of the first tube. You have the plate at the top, cathode at the bottom. This is the cathode resistor R2 with the bypass capacitor C2. You have the B plus through the R4, so that goes to the plate. Here it's usually the B plus is on top, but here there's no room, so I put it below, but that's the same idea. So that's an amplifier, that's the output signal, goes through coupling capacitor C4 and R6, R7. So the output here is developed across R6 and R7. So this is your voltage, which is shown here. And here, so you have amplification, so the greater magnitude, and you have inversion. Remember that for any tube amplifier, you have inversion at the output because you are looking at the plate. Remember that there is a minus in the equation for the voltage, so that's why you have inversion. You always have inversion. So that's your output. And what you do is that you take a portion of that output, namely the one here, this one, the one developed across R7, and this is gonna be the input. This is gonna be the input to that second amplifier. So what you need to do is you make sure that R7 is such that this signal here is the same in terms of amplitude as this signal. They are 180 out of phase, but they have the same amplitude. And of course, this assumes that the two amplifiers have the same amplification factor. So anyway, so that's your input to the second amplifier, and this is exactly the same setup. Again, you have your plate here, cathode resistor, bypass capacitor. You have the B plus that connects to the plate through R5, just like here. And then the output goes through the coupling capacitor C5, and it develops a voltage across R8. So because of that double inversion, so you have one inversion here, and of course you have another inversion because of the amplification. So this one is inverted with respect to this one, or 180 out of phase, but it is now in phase with this input here. So here are the two outputs. Okay, so you have one here and one there. Okay, so this is your ground here. And they have the same magnitude. They have been amplified, same magnitude, but they are 180 out of phase. And this is fed to your push-pull amplifier. So it looks complicated, but it's a very, very simple circuit. So anyway, I'm going to stop here. And I'll see you around. Bye.